Welcome back to the Deep Dive. Today we're jumping into something really fundamental, a concept that shapes things all the way from tiny particles right up to the sun itself. We're talking about the magnetic flux tube.
Mhm.
Yeah, our goal here is to, quickly get a handle on what it is, look at some massive examples out in space, and then touch on this, frankly, surprising role it plays down at the quantum level. It's kind of a universal shortcut for understanding how energy and matter get channeled.
It really is. And it's important to remember these aren't just diagrams. Flux tubes, they're real physical structures. They're like the universe's plumbing, guiding energy, guiding matter across just vast distances. Understanding them gives you this powerful lens on how things are organized.
Absolutely. And speaking of support, this deep dive is brought to you by embersilk.com. Okay, let's get into it. Let's start right at the beginning. What is a magnetic flux tube? What makes it a tube?
Okay, think of it like this. You have magnetic field lines, right? Imagine bundling a set of those lines together. The tube is the surface that contains that bundle. And crucially, the sides of this tube are made of the field lines themselves. So nothing magnetic crosses the sides.
Ah, so it's self-contained. And the flux part relates to the amount of magnetic field passing through it.
Exactly. The total magnetic flux, think of it as the total magnetic flow passing through any cross-section of that tube, stays the same along its entire length. That's the fundamental property.
And that's where the power comes in, isn't it? That constancy rule.
Precisely. Because if the flux has to stay constant and you squeeze the tube, you make its cross-sectional area smaller, then something has to give.
The magnetic field inside has to get stronger to compensate.
It has to skyrocket proportionally.
Yeah.
Squeeze the area by half, the field strength doubles. This is how magnetic fields naturally become incredibly concentrated in certain regions.
So this simple geometric idea, keep the flow constant, leads directly to these points of intense magnetic power. That makes sense.
It explains so much. And, sometimes these tubes can get twisted up on themselves. We call that a flex rope.
A flux rope. Basically a twisted tube holding even more energy.
That's right. It stores magnetic energy in that twist. And this kind of structure, this intensification, it plays out dramatically on the sun.
Right. You mentioned the sun. Sunspots seem like the obvious example here.
They're a perfect visual.
Mhm.
Sunspots are essentially the footprints of enormous flux tubes punching through the sun's visible surface. We're talking tubes maybe 60,000 kilometers across.
Wow.
Yeah, and the fields inside can reach, 3,000 gas. That's incredibly strong. These structures, especially the twisted flux ropes, are also key players in things like coronal mass ejections, huge solar eruptions.
And also the coronal loops we see, those giant arches of plasma.
Those too. Plasma gets trapped along the field lines within these arching flux tubes, outlining them beautifully. The fields there are weaker, maybe 0.1 to 10 gas, but still shaping the corona.
Okay, so massive solar examples. But it's not just stars, right? You mentioned planetary connections too.
Oh, absolutely. One of the most, frankly, spectacular examples is the flux tube connecting Jupiter and its moon Io.
The volcanic moon Io. So there's a persistent magnetic link.
A very real, very powerful one. It channels energy between them constantly. Near Jupiter, this tube is estimated to be about 450 kilometers in diameter. It's like a planetary circuit.
That's incredible. A 450-kilometer wide magnetic conduit. Okay, so we've gone from the sun down to planets. But now you're saying the same concept applies at the other extreme, down at the particle level.
This is where it gets really mind-bending, I think. We shift from astrophysics to particle physics. We look inside things like protons and neutrons, particles called hadrons.
Which are made of quarks.
Right. What holds those quarks together? The strong nuclear force. Now, unlike gravity or electromagnetism, the strong force doesn't just, spread out everywhere.
It behaves differently.
Very differently. The field lines of the strong force actually bundle together into incredibly thin flux tubes between the quarks. Think maybe a billionth the size of the proton itself.
Tiny tubes of pure force.
Exactly. And here's the twist. Because of the way the strong force works, that constant flux idea leads to something called color confinement. If you try to pull two quarks apart,
The tube stretches.
and the force holding them together actually gets stronger, not weaker, the further apart they get. It takes more and more energy.
So you can't pull them apart. The tube just resists more and more.
Precisely. It's like an unbreakable rubber band. That's why we never ever see a quark by itself in nature. They're always confined inside particles by these flux tubes. It's the structure itself that ensures confinement.
Wow. So this single concept, the flux tube, scales from holding quarks together inside a proton all the way up to structuring solar flares and linking planets and moons. That's quite a range.
It covers about 24 orders of magnitude in scale. It really underscores how fundamental field structures are in organizing the universe. A concept tracing back to Maxwell helps us understand everything from, say, fusion energy experiments to the basic stability of matter. It points to a deep unity in physics.
It really does. Okay, so here's something to think about. We see fields organizing matter into these tube-like channels everywhere we look, from the incredibly small to the astronomically large. If this principle is so universal for electromagnetism and the strong force, where else might it be hiding? Could gravity maybe organize things into structures we just haven't recognized as tubes yet? Something to ponder. Thanks for joining us on the deep dive.